Hello everyone. Have you ever wondered why a ray of sunlight forms beautiful patterns when it passes through a narrow slit, or why the colors dance in soap bubbles? Well, that's where wave optics steps in, and it's quite the superstar compared to ray optics. Imagine ray optics as the strict math teacher, treating light simply as straight lines that travel in one direction. It nails lots of things like reflection and refraction, but it completely misses out on explaining cool effects like diffraction and interference, where light bends and overlaps in fascinating ways. That's why wave optics was born. This theory treats light as a wave, allowing waves to add up or cancel out through a process called superposition. In wave optics, we consider light as transverse electromagnetic waves where electric and magnetic fields oscillate at right angles to each other and to the direction light moves forward. This wave picture is essential because experiments, like the famous Young's double-slit experiment, show fringe patterns that simply can't be explained by treating light as straight rays. These patterns are clear evidence that light has wave-like behavior, pushing us to embrace wave optics for a deeper understanding of nature's light show. Alright, let's dive into the origin story of wave theory. Way back, Huygens introduced a brilliant idea. Every point on a wavefront isn't just sitting idle, it acts as a tiny source sending out secondary spherical wavelets. The new wavefront you see is actually the envelope formed by all these little wavelets combining together. Fast forward to Maxwell, the genius who revealed that oscillating electric and magnetic fields don't just coexist, they actually sustain each other, marching through space as electromagnetic waves. And here's a neat fact: light travels at speed c, which is 1 divided by the square root of the product of the vacuum's permeability and permittivity. That's the fancy way of saying the speed of light depends on electric and magnetic properties of empty space. Light waves have electric and magnetic fields that oscillate perpendicular not only to each other but also to the direction in which light travels, forming a truly transverse wave. This wave theory elegantly explains phenomena like interference, diffraction, and polarization, confirming that light is indeed a transverse electromagnetic wave. So, thanks to these visionary scientists, we understand light in a much richer, wavy way. Now, let's look at what makes light waves tick, their properties. Light waves have a wavelength, symbolized by the Greek letter lambda, which is basically the distance between two peaks of the wave. Frequency, labeled f, tells us how many such peaks pass a point every second. There's also the wave number k, which is 2 pi divided by wavelength. Think of it as how many waves fit into a unit length. And phase, denoted by phi, tells us the position of the wave at a certain time and place. The electric field of a light wave in free space can be described by the equation E of x and t equals E naught times sine of open bracket k times x minus omega times t plus phi close bracket, where E naught is the maximum field strength, k is the wave number, omega is angular frequency, t is time, x is position, and phi is phase. The relations V equals f times lambda, omega equals to pi times f, and k equals to pi divided by lambda connect these properties mathematically. Here's a key insight: unlike sound waves, which need air or another medium to travel, light waves can zoom through vacuum, proving their electromagnetic nature. Picture a diagram where the electric field vector points up, the magnetic field vector points sideways, and both are perpendicular to the direction of propagation. That's the beauty of electromagnetic wave orientation. Let's get into coherence and phase, the backstage pass for glorious interference patterns. Coherent sources produce waves that keep a steady phase difference and share the same frequency. Imagine two drummers perfectly in sync, beating the same rhythm. This constant phase relation is vital for interference patterns to appear stable and sharp. To get the most striking fringes, the waves must also have nearly equal amplitudes, otherwise the pattern gets fuzzy or dim. The intensity of the combined waves, denoted I, equals I1 plus I2 plus 2 times the square root of I1 times I2 times cosine of delta phi, where delta phi is the phase difference between the waves. This formula tells us how bright or dark the combined light will be depending on phase. Both spatial coherence, meaning the waves come from sources close enough to maintain overlap, and temporal coherence, the waves maintain consistent phase over time, are necessary to observe the stable fringes you see in experiments like Young's double-slit setup. Imagine the diagram showing two-point sources labeled S1 and S2 shading wavefronts that overlap and create patterns governed by their phase difference phi. This visualization helps us grasp how coherence shapes the light show. Now, here's a nifty principle that helps us understand how waves move and change direction, Huygens principle. It says every point on a wavefront acts as if it's a tiny source sending out its own secondary wavelets. The new wavefront forms as the envelope or outer boundary of these wavelets. This simple idea doesn't just explain wave propagation, it also cleverly accounts for reflection and refraction as new wavelets build up in new directions. When light passes from one medium to another, wavelets travel at different speeds, and applying Huygens' construction along with Fermat's principle leads us to Snell's law. This law states that the sine of the angle of incidence divided by the sine of the angle of refraction equals the ratio of speeds in the two media, which is also equal to the ratio of their refractive indices. Picture the diagram, an incident wavefront approaching the boundary at an angle I and bending into the second medium at angle r with speeds v1 and v2 labeled accordingly. Thanks to Huygens, we've got a wave-based foundation for the laws of geometrical optics. Time to shine the spotlight on interference, the playful superposition of light waves. When two coherent waves meet, the amplitudes add up, resulting in variations in light intensity you can actually see as bright and dark fringes. The condition for bright fringes, or constructive interference, is that the path difference between the waves equals an integer multiple n of the wavelength lambda. For dark fringes, or destructive interference, the path difference is n plus 1/2 times lambda, which means the waves arrive out of phase and cancel each other. The resulting intensity I of the combined waves equals I1 plus I2 plus 2 times the square root of I1 times I2 times cosine of the phase difference delta. This equation beautifully captures how waves strengthen or weaken each other. Importantly, interference patterns like these prove light's wave nature, because if light were just particles, we wouldn't see alternating dark and bright bands. Picture the classic Young's double-slit interference pattern on a screen, with the stances labeled D for the screen, D for the separation between slits, Y for the position on the screen, and lambda for the wavelength of light. This setup reveals the secrets of wave superposition right before your eyes. Let's wrap up what we've explored today. We learned that the speed of light c equals 1 divided by the square root of the product of vacuum permeability μ0 and permittivity ε0. The electric field of a light wave can be described by E of x and t equals E0 times sine of open bracket k times x minus omega times t plus phi close bracket, capturing how light oscillates in space and time. The wave number k equals to pi divided by the wavelength lambda, and angular frequency omega equals to pi times the frequency f, tying these characteristics beautifully together. Finally, interference intensity I equals I1 plus I2 plus 2 times square root of I1 times I2 times cosine of the phase difference delta phi helps us understand the bright and dark fringes we observe. Wave optics opens the door to understanding light's marvelous behaviors beyond straight rays, from shimmering colors in a soap bubble to the precise workings of lasers and optical instruments. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.